I've written down two functions for which I'd like to find the derivative. Y equals the sine of x cubed and y equals the fifth power of log x. I hope you recognize that these are examples of things called composite functions. That is, one function nested inside another. For example, we could write a composite function as y equals f of g of x. In our two examples, well, in number 1, f is the sine function and g is the cube function. While in number 2, the f is the fifth power function and the g is the log function. In this MathsCast, I'm going to assume that you've already been taught a little bit about differentiating such functions. In particular, I'm going to assume that you know that the right rule to use is the chain rule, and that your teacher will have shown you one way of doing that. The way most people learn this first is to use a substitution. They say, let g of x be called u. So now y is f of u, where u is g of x. And then they're taught that we differentiate making a chain through the functions. So dy dx is dy du du by dx. We can think of there as being a sort of chain from y via the u derivative ending at the x. In practice, for our two examples, in the first case we would let u equal x cubed, so y is sine u. Let's write them down. 1. Y equals sine u, where u is x cubed. So dy dx is dy du, du dx, and dy du is cos u, and du dx is 3x squared. But then, because u was something we introduced, we replace it with what it really should be, which is in this case x cubed. So that's altogether 3x squared cos of x cubed. Similarly, in number 2, we have y is u to the power 5, where u is the log of x. And so dy dx is dy du, that's 5u to the 4, times du dx, which is 1 over x. So that's altogether 5 log x to the power 4 divided by x. Now, there's absolutely nothing wrong with this method. I'm not knocking it, and it's quite important to know that this is how things work. But what I want to show you now is that you don't really have to go through all this procedure of introducing a u. Let's look at the answer in the first case. 3x squared cos of x cubed. What has actually happened here? Let's write our function up here again. Y equals sine of x cubed. Suppose I couldn't be bothered to introduce a u. What has really happened here? Well, we've got cos. Cos has come from differentiating the sine. And the thing inside the cos is the same, still x cubed. But then, outside here we've got a 3x squared, and that's just the derivative of the x cubed. So we didn't really need to use u at all. We could simply say, OK, let's step through the functions in turn. First differentiate the sine, we get cos. Then multiply by, and now we go inside the sine. The sine is finished with. We differentiate the x cubed, and we get 3x squared. In exactly the same way, in case 2, the alternative would be just to write y equals log x to the fifth. Now let's describe the function to ourselves. It's a fifth power function of log of x. So we differentiate the first function, that's the fifth power. dy dx is, with the fifth power we just need the power law, 5 log x to the 4. Now the fifth power is finished with, it's said what the derivative should be, but inside there's a log x just dying to express its opinion. Log x says the derivative should be 1 over x. And so there's our answer, without introducing u. It has saved a little bit of time and thinking. In fact, this method, without any substitutions of u's, v's or whatever, can be used and extended to long nests of functions. So let me show you the utility of this method now by looking at an example 3. Let's make it really complicated. It's y equals log of sine of the square root of e to the power tan x plus x squared. That's a composite function, but it's not just a composite of two functions. It actually involves 4 functions: the log of, the sine of, the square root of, and then the special combination e to the tan x plus x squared. I could introduce a u, a v and a w and write this as log of w, where w is the sine of u, where u is the square root of v, where v is e to the tan x plus x squared. It would work. I'd make a long chain, dy, dw, dw, du, du, dv, and so on, and I'd get there in the end. But I don't have to do that. All I really have to do is use the technique I showed you above. We differentiate each function in turn using the rule appropriate for that function. So first of all, we see outside it's primarily a log of something. The rule for log is 1 over. So we just get 1 over, and then the sine of the square root of e to the tan x plus x squared. That's dealt with the log. It's finished with. We can forget it. Inside the log is a sine. When we differentiate sine, we always get a cos. We get a cos of whatever was in that sine. There we are. Now the sine is finished. Now inside that sine is a square root. I hope you can picture that that square root is, of course, a half power. So we can use the power law on it. So multiplied by 1/2 e to the tan x plus x squared to the power negative 1/2. That's finished with the square root. Now what's left? E to the tan x plus x squared. When we differentiate an exponential, we get the same exponential. But inside that exponential is a tan. We differentiate that and get a sec squared. There's just the x squared left. That gives 2x when we differentiate it. And so there's our derivative. I admit it's very complicated, but then the original function was quite complicated. The nice thing is that, although the derivative itself is complicated and messy, the process of getting it was very straightforward. I recommend this method to you for using the chain rule. Certainly it's important to understand the process involving substitution with u's and possibly u's and v's and w's if there are lots of composite functions. But in actually handling the chain rule and performing the process, I recommend the method that I've shown here.